Welcome to this Oracle Cloud Partner Webinar, Provisioning Oracle Cloud Infrastructure with HashiCorp Terraform. First, I just want to cover our standard safe harbor statement. Any forward-looking statements made during this webinar are for information purposes only and should not be considered a commitment to deliver, and timing on anything mentioned today may change. My name is Stephen Cross, Director of Product Management in the Oracle Cloud team, responsible for our partner ecosystems and the Oracle Cloud Marketplace programs. It's been my pleasure to have been working very closely with HashiCorp as we build out support for the HashiCorp toolset across the Oracle Cloud, and specifically HashiCorp Terraform, which is the topic for today's discussion. With me today is Berzin Patel, Vice President of Alliances at HashiCorp, as well as Jake Champlin, who is a software engineer who works on the Terraform ecosystem. For our agenda today, we'll be giving a brief overview on the Oracle Public Cloud and why we've been working with HashiCorp specifically. And then I'll invite Berzin and Jake to give more detail on HashiCorp, the Terraform integration, and we'll go through a demonstration. At the end of the presentation, we'll have some time for some Q&A. So first, let me start with why we've been working with HashiCorp. I hope most people on the call today are already familiar, at least at a high level, with the breadth of offerings in the Oracle Cloud with our data as a service offerings, software as a service with customer experience, human capital management, ERP, supply chain, and others. The platform services for Oracle Database and Java Cloud, as well as many other platform components and integration capabilities. And then our infrastructure as a service, offering a global compute, networking, storage, and other complementing capabilities, which is going to be the main focus for today's session as we talk about provisioning the infrastructure. In addition to the capabilities offered by the Oracle Cloud, Oracle has a long history of partnering with ISVs and other technology partners to offer complementary and supporting solutions around the Oracle technology and around the Oracle Cloud products. We have a very strong ecosystem around the cloud where we have many partners offering integrations and applications that run on the Oracle Cloud services all the way across the Oracle Cloud technology stack. For more information on these, you can go to cloud.oracle.com/marketplace. Our focus today is on HashiCorp and the work we've been doing around infrastructure and infrastructure provisioning. So as you look at these infrastructure services from the vantage point of the developers, DevOps, architects, and IT operations, they're looking to incorporate these services into the tool sets that they're already using or adopt the latest industry best practices, whether that's to lift and shift applications to the cloud. You're looking at maybe a whole data center migration to the cloud, could be incorporating the tools and services into existing continuous integration and continuous deployment pipelines, or you're looking to build and evolve cloud-native applications. All of these need a coordinated approach to provisioning not just the infrastructure components, but the complementary platform components, the application components that are needed to deliver the overall solution. And this is where HashiCorp's Terraform fits in as a tool that can be used to describe and orchestrate and deploy the services not just across the infrastructure components, but coordinated across the platform and other external services that are needed in order to deploy and configure the overall solution delivery in a very consistent and repeatable manner. So I'm pleased to announce that Terraform now has native support for the Oracle Public Cloud with the ability to provision Oracle Compute Cloud services. And this capability that we are continuing to work very closely with HashiCorp to evolve across the Oracle Cloud platform, as well as looking across the rest of the HashiCorp toolset. So with that, let me now hand over to Berzin Patel from HashiCorp to provide an overview of where Terraform fits within the overall HashiCorp suite of tools. Over to you, Berzin.
Thanks, Stephen. Hello, everyone. Given that HashiCorp may not be familiar to many of you all, it may help to start with a quick background. HashiCorp was founded about 5 years ago by Mitchell Hashimoto and Armand Dadkar. What Mitchell and Armand observed as op practitioners was that as customers moved from a static infrastructure to dynamic cloud infrastructure, there was a real gap in the tools across the different aspects of the software delivery process. In principle, the tasks required of the ops practitioner to provision, secure, and run their infrastructure were the same as those performed for traditional infrastructure, but just needed to be attuned to the challenges of a cloud and distributed infrastructure world. That was the genesis of HashiCorp, to build a product suite for practitioners to help them provision, secure, and run hybrid cloud application infrastructure without tying themselves to a particular platform or technology. We often find that the company is better known for its products than the name. The most popular of these, of course, being Vagrant, which was our first product and has millions of users. However, Terraform, Vault, Console, and Nomad have grown in usage as well and now have more than 40,000 unique downloads per week, a stat which has doubled in the past 6 months. We're excited to have OPC supported with HashiCorp Terraform. Oracle and HashiCorp share many common customers, primarily the Fortune 2000. From our perspective, there are really two main things going on with these customers. They're increasingly interested in migrating their workloads to the cloud to leverage the price and elasticity advantage the cloud has to offer, and they're looking to accelerate their application delivery. We often see these two trends work together. However, it's important to acknowledge that they're two very different problem areas. This is at the core of what HashiCorp enables and what Stephen referred to earlier as cloud lift and shift, or adopt cloud, and cloud native, often referred to as DevOps, which is really a way to enable the developers, operators, and security folk to work in parallel. The HashiCorp products are at the center of both these, and that explains the ubiquity of the adoption. Let's dig into each of these independently. So let's first talk about the cloud adoption scenario and how we think about it. The world is broadly looking to go from here, which is a traditional data center running servers with some local storage, possibly vSphere, with apps on top, to this, which is this new world which pretty much every company is going to. Now, as they make this transition, they're looking for a blueprint of how to navigate the transition and simplify the process. In our experience, the way they do this is by breaking the problem up into its components. At the base level, there's the core infra, the servers, the storage, the network. On top of that is the application platform. This is really where the developers are engaging and includes things like app servers, databases, messaging queues, which could be container-based, VM, or multi-platform. Basically, a lot of heterogeneity. The ops team is standing up the core infra and making it available to the developers. Some notion of security is then wrapped around the core infra and the app infra, typically with a firewall, making everything inside impenetrable. As people try to navigate from that to this, what we find is that they approach the problem in a very similar way. Step one is to determine the core infrastructure capability they'll need to plan in a multi-cloud environment. They know they might be going to Oracle, but also know that over time, they'll most likely need to support other infrastructure due to some acquisition, pricing, or cloud capability. They then think about how they need to decompose the application platform as step two. There may be a need for some legacy applications, container applications, maybe even an application platform, something like a Kubernetes. Practically, this is just how things pan out. Lastly, they need to figure out security, given that the notion of a firewall no longer makes sense with the dynamic nature of the cloud infrastructure. Architecturally, if we were to simplify this to its core, there are really four elements: infra at the bottom, the security layer, and the runtime layer. There is also a fourth element in modern infrastructure, and that is the common backbone that catalogs the dynamic infrastructure, which may include tens or hundreds of thousands of dynamic nodes. How we think about this is there's an infra layer the team needs to provision, a security layer for security, a runtime layer, and then a connect layer to connect them all. Now, how our product portfolio has evolved is to focus on the four elements of modern infrastructure. Vagrant, which has millions of active users, is about provisioning single-user desktop infrastructure. Packer is an environment-agnostic way of provisioning images, and Terraform is a tool for building out the infrastructure. Taken together, these tools provision infrastructure. Above that is a security layer. Vault is the tool that addresses the security challenge. And on top of that is Nomad, which is a scheduler, and Console, which provides the common backbone. These are the challenges of running modern infrastructure, and our products are really Lego pieces, each of which can be used individually or mix and matched. Think of these as a suite of products, not a platform that has to all be consumed at once. This is how our product portfolio works in the open source world. We also offer commercial product offerings around the same tools for our enterprise customers. For example, we add features like collaboration in Terraform, replication in Vault, and multi-cluster support with Console. So that's one way our tooling gets used. The second business driver is users who are looking to accelerate their application delivery, often referred to as DevOps. So let's take a look at this. In the traditional way, users deliver applications in very much a waterfall model. Developers develop the application, security teams define policies, and then the infrastructure gets provisioned. In this model, devs are often waiting hours, days, or sometimes even weeks on the security and the infrastructure teams. Herein lies the challenge: devs getting bottlenecked by downstream tasks. What we're looking for is to try to get to a model which parallelizes all three stages of the workflow to be able to deliver applications more quickly. In a sense, that is what DevOps is about. So let's just very briefly talk about the application delivery process. Every application starts the very same way. Someone has to develop the application, and someone has to test it. After that, someone needs to package the application into the environment-specific version. For example, the Oracle images are packaged into a gzip format. Then someone needs to provision the infrastructure, the server, storage, networking, and any other components that may be required. Then they need to ensure that the environment is secure. And lastly, they need to deploy and monitor the application. These are the 7 elements of the application delivery process. These haven't changed for a long time and probably will remain the same in the future. What the team at HashiCorp has done is to build tools that are applicable to each of these elements. So if you need to build an environment for your development, that's Vagrant. If you need to package, that's Packer. Deploying infrastructure is Terraform. Securing your environment is Vault. And running the application is done by Nomad and Console. So when you think about this architecturally, you start to see why these two problem domains are so commingled. This idea of cloud adoption and DevOps adoption. This is because a common tool set is being used to support both of these. What you see is a stack that permits a user to define their infrastructure as code in a version control system like GitHub at the bottom of there, and have that be deployed in OPC at the top. Architecturally, this holds true. You fundamentally have to provision infrastructure, secure infrastructure, and run your applications. This is a prerequisite at the tooling level for the adoption of DevOps. And as I mentioned, we have commercial products of the open source tools. For the rest of the session, we're going to be focusing just on the infrastructure deployment piece with Terraform. I'll now hand it off to Jake to walk us through that.
Thank you, Berzin. My name is Jake Champlin, and I am an engineer on the Terraform ecosystem team at HashiCorp, and I'm here to talk to you today a little bit about Terraform. Terraform enables you to safely and predictably create, change, and improve production infrastructure. It is an open source tool that codifies APIs into declarative configuration files that can be shared amongst team members, treated as code, edited, reviewed, and versioned. Terraform is a multi-provider tool, meaning that this one tool allows you to spin up multiple resources on multiple different cloud providers at the same time. It also has an internal resource graph that is able to correctly order the number of dependent resources in a highly efficient manner. Terraform also enables you to plan, collaborate with coworkers, and execute changes to your live infrastructure. First, let's talk about infrastructure as code. With Terraform, we had a number of goals. Primarily, with infrastructure as code, your configuration designs your desired state, and your code becomes the single source of truth. We wanted to support a modern environment composed of physical, virtual, and containerized infrastructure, including PaaS and SaaS. Operators should have confidence in the changes that they're making. Lastly, operators should have one workflow for managing their infrastructure, regardless of the underlying technology. If it has an API, Terraform can manage it. Terraform can parse both HCL, which is a HashiCorp configuration language, as well as JSON, allowing the user to have full control over their source files. Text format files allow engineers to store their configuration in any VCS that they are comfortable with. Here's an example of a Terraform configuration file. First, we declare the configuration type, the resource type, and then the resource name that is used within Terraform. Inside the configuration block, we list all of the necessary attributes needed to create our specific resource. Here we see that we are creating a storage volume inside the OPC Compute Cloud called test. We give it a name and a size. Second, we declare another resource block that creates an OPC instance called server. We give the correct attributes, the name, the shape, and the image list needed to create the OPC instance. We also specify an optional attribute block called storage, which in this resource's case allows us to mount the previously created storage volume to the OPC instance. Assigned to the volume attribute is an HCL interpolation. Interpolation allows users to use computed values and exported attributes from other resources to create dependent resources with ease. Thus, if the name of the storage volume was ever changed, the user would only need to modify the name of the storage volume a single time. Next, let's talk about the plan, collaborate, and execute workflow of Terraform. Let's start with Terraform plan, as it will likely be the first command that you use before you make any change to your infrastructure. A Terraform plan will show you, the operator, what Terraform plans to do before doing it. You can then decide to continue with the changes via a Terraform apply, or make further changes to your configuration if you decide the plan does not have the intended effects that you need. Terraform plan removes the guesswork of what changes are needed and what they will look like once they have been made. This builds confidence and trust in your infrastructure operations. You can also save a Terraform plan to guarantee what will happen during the subsequent Terraform apply. Using the same Terraform configuration that we had earlier, we can see what the output of a Terraform plan looks like. In this output, the plus sign indicates that a resource will be created. We can see the supplied properties for each resource, the computed properties, meaning the ones that the provider will determine for us, and any properties that reference other resource properties are displayed. For example, the OPC instance has yet to be created, and Terraform doesn't know what the IP address of the instance will be yet, so it shows that this attribute will be computed. At the end of the output, we see a summary of the changes. In this case, 2 resources will be added. We can also see that the storage volume name was interpolated correctly inside of the OPC compute instance called server. The next step in performing changes with Terraform is to perform a Terraform apply. The apply is when the infrastructure operations are actually performed. Prior to this, no infrastructure has been modified or changed. Using the resource graph defined by our configuration, Terraform determines the order in which to perform our changes, parallelizes the change when possible, and will handle any known timing and transient errors where it can. As an example, for a more complex configuration, Terraform can create multiple OPC instances in parallel and will handle any provider errors that may occur. Here we see the output of a Terraform apply, using our same configuration as before. We can see the same resources being created and in the necessary order. For instance, we can see that the storage volume called test was created prior to the OPC instance. This is because the OPC instance has a dependency on the storage volume called test. Terraform natively knows which resources need to be created first due to the internal resource graph that it uses. Again, lastly, we see a summary of the changes showing that our 2 resources have been created, 0 resources have been changed, and 0 resources have been destroyed. Once we are ready to destroy our resources, we can perform a Terraform destroy. Similarly to a Terraform apply, Terraform destroys all of our resources in the necessary order, destroys appropriate resources in parallel, and handles any known provider errors. It is important to know that you can see a plan of the destroy prior to running it by running Terraform plan with the destroy option. Here we see the output of a Terraform destroy using our same configuration as before. We can see that the same resources are being destroyed and in the necessary order. We can also see that the user has to type the full word yes in order to destroy the Terraform resources during the prompt. This is to help ensure that no infrastructure is accidentally destroyed, causing any adverse side effects to your infrastructure. Now, let's look at a quick demonstration of Terraform using the same workflow that we discussed earlier. Okay, so if we look at a Terraform configuration file, in this case main.tf, we can see that we are creating multiple different Terraform resources. First, a OPC compute storage volume and an OPC compute IP network. We're also creating an OPC compute instance called server. We are attaching a storage volume to the OPC compute instance that we created earlier, as well as attaching a network interface to the OPC compute instance that we also created earlier. This is because of the HCL interpolation language that can interpolate values inside the Terraform configuration file. We're also creating an OPC compute security protocol and an OPC compute security rule that includes the OPC compute security protocol that we created earlier. Next, if we run Terraform plan, we should see that all 5 resources are planned to be created. We can see that the resources are going to be created by the plus sign in the output. In this case, we can also see that the OPC compute instance called server is going to be successfully created. Next, if we run Terraform apply, we should see all of the changes propagate as Terraform makes the correct API calls to create all 5 resources. This may take a while, so we are going to fast forward for a little bit. Okay, now we see at the bottom of the output that Terraform was successfully able to create all 5 resources. Next, if we run a subsequent Terraform plan, we should see that the Terraform configuration file and the Terraform state file are in sync. This means that there are no changes that need to be made to our code. Our infrastructure is up to date. If we want to add more resources to our Terraform configuration file, say for instance an OPC compute IP network, we can add this here, and then if we run a Terraform plan against this new configuration, we should see that the new resource should be created. And as we can see, Terraform registered a diff between the configuration file and its state file that we need to create a new OPC compute IP network. So when we run Terraform apply on this configuration, Terraform will make the necessary API calls to create the missing IP network. Awesome, the final resource has been created. Next, if we run Terraform show, we should be able to get a snapshot of all the resources that Terraform knows about and has created, as well as all the information associated with these resources. For instance, the OPC compute instance and both OPC compute IP networks, the initial one that we created, as well as the second one which has been added. Finally, if we want to destroy all of the resources in our save file, we type Terraform destroy. Terraform will prompt the user if we actually do want to destroy our resources, and upon hitting yes, Terraform will destroy all 6 resources, and we can see that that completed successfully below. We can validate that Terraform did destroy all of the resources by running a final Terraform show. The nil output shows that Terraform doesn't know about any resources. Next, let's take a look at Terraform Enterprise. Terraform Enterprise allows you to run all of your Terraform plans and applies in a distributed environment. It also locks Terraform environments natively, such that parallel Terraform runs cannot happen against the same Terraform environment. This helps prevent any unknown resource duplication and errors. Terraform Enterprise utilizes change management and well-defined ACLs in order to further prevent accidental infrastructure provisioning errors. You can create users, organizations, and assign the correct user permissions needed to give full infrastructure control to your team. Terraform Enterprise also utilizes native VCS integration, such as GitHub and Bitbucket, with many more to follow. This allows Terraform Enterprise to run Terraform plans on pull requests and merges and more. Here we show an example of a user's perspective when using Terraform Enterprise. We can see all of the Terraform environments that that user has access to, as well as the health status of Terraform Enterprise. Here we can see the output of a Terraform plan inside of Terraform Enterprise. We can see that the Terraform plan was queued, started, and ran. We can also see that a coworker commented on the plan, stating that the Terraform plan looked good and that the run was confirmed by a user. Next, we can see that the apply was then queued, started, and is currently running. We can also see that each step of the workflow is timestamped, and user interactions are also linked to provide full control and collaboration between your entire organization. Finally, we can see that the Terraform apply executed successfully and that Terraform exited without any errors. This Terraform run is also saved inside of Terraform Enterprise, allowing other users to audit exactly when an infrastructure change occurred and escalate if any problems occur as a result of this change. Since both the plan and apply outputs are also shown inside the Terraform run, this gives organizations a full snapshot of every change that has ever been made to their infrastructure. We can now see just how powerful Terraform and Terraform Enterprise can be when managing production infrastructure.
Thank you very much, Jake. So as we continue to address any final questions in the Q&A chat, I just want to highlight that you can find a lot more information by going to the main Terraform website at terraform.io, where you can download the latest distribution that includes full support for the Oracle Public Cloud, Oracle Compute Cloud provider. There's also full documentation on how to use the Oracle provider available on that same site. And for any questions and issues around using the provider, you can submit those through the HashiCorp Terraform GitHub repository. And with that, I just want to say thank you very much to everybody for joining the webinar today. Thank you very much to Berzin and to Jake for providing us the overview and introduction to using Terraform with the Oracle Public Cloud.